Hello everyone, my name is Ramon Imad and I'm a PhD student at CDC IPN. Today I will be presenting to you our paper entitled Prescribed Time Robust Differentiator Design using Finite Variance from Dr. Judy Orlov from CDC and myself and Dr. Luis Tupac Aguilar from CDC IPN. The outline of the presentation is divided in 6 items, and I would like to go straight forward with the introduction. Typically in closed loop system, when we want to decide the controller, we can have two possibilities. First is full information. This means that all states are available for feedback design, so the controller can be designed using this entire state information. In the other hand, sometimes we only have output information, so an observer is needed to recover the state information, and this estimation is presented here by hat x. Next, with this information, we can design an output feedback controller. So these two are typically closed loop systems in control design. We focus ourselves here in the observer design. So what are the challenges in observer design? First, the convergence should be guaranteed irrespective of the observer initialization. Also, a certain convergence rate should be required for the observer to rapidly generate accurate estimates of the state. The estimate needs to be accurate even in the presence of model uncertainties. And finally, the quality of estimation should not be too sensitive to measurement noise. In the literature, the first 3 items are expressed or are met by high gain observers and also finite time observers. Meanwhile, the second, third, and fourth are met by Kalman filters typically. So, what's the motivation behind the prescribed time observer design? There are some applications with critical convergence times, as I'm showing here in these 2 figures. For instance, the working of a biped robot, we need to recover information of the states before each step. So this is a critical time window that must be fulfilled. And also in this case, I'm showing here the intersection of a missile, and it is also very fast and requires accurate estimation of the state vector in some time window. Let us formalize then the problem statement in the following slide. We will consider only a second order system, as we can see here in this plant figure, where x1, x2 are the state vector, x1 is the only available measurement, the output of a system, f is a known input, and phi is collect disturbance entering the system in the matched form. The assumption throughout is that the external disturbance phi is uniformly bounded, as we can see here in this inequality, by an upper bound, capital Phi, a priori known and constant. The problem per se is to exactly estimate the state velocity x2 over the available position measurement x1 in prescribed time, capital T, greater than 0, selected a priori and independently of the initial conditions of a system, regardless also of whichever admissible disturbance affect the system. Alternatively, it might be viewed as to exactly differentiate the signal x1 in prescribed time, selected a priori and independently of the initial conditions of the system, with the disregarded input f and with the disturbance term standing for measurements imperfections. Our solution then is called hybrid observer, and in this next slide I will show the synthesis of this hybrid observer. The hybrid observer is shown in equation 1, which typically is a copy of the known dynamics of a system plus injection terms we call it here capital G1, capital G2, which are given by this hybrid terms that switch the structure once the sliding mode is detected with the available information, that is the observation error E1. So E1, E2 are the position and velocity observation error components of the error observation error vector E. Mu1 is the time varying gain that tends to infinity as the time approaches to capital T, and alpha beta positive constants respect inequality that I'm presenting here. The synthesis of this time varying substructure I will try to show here in a few steps. We start from the observation error dynamics in the S time variable. The S time variable is given here in this first line. It's a mapping from the semiopic interval 0 capital T to 0 capital infinity. So this here in the left is well-known supertwisting, and with the particularity that the perturbation disturbance term is pre-specified in this way. Well, the upper bound of this term also satisfies that it's the same upper bound of phi. So by applying the time and state transformation that I'm proposing here in the right to this dynamical system here, we get the representation of the observation error dynamics in the time variable t. So from here it's easily to get the injection terms capital G1, capital G2 as I'm showing here. Let's say the non-autonomous injection terms. Of course, once the system switches the structure, we get the well-known autonomous supertwisting injection terms. Let us now present the main result of our paper in this theorem. Consider the double integrator 2 affected by disturbances phi and a known input f, and its observer 3 designed with the injection terms capital G1, capital G2, with an arbitrary small capital T independent of initial conditions and admissible disturbances. The aerodynamic 4 are then fixed time stable with a convergence time capital T sub 0 lower than capital T, and with a bounded time varying gain mu1 applied at the initial stage 0 capital T sub 0 only. This section is devoted to describe a time velocity estimation of a mechanical system. In this case, we are using the pendulum system as I'm showing here in the right, with this dynamics, where q is the angular position, dot q is velocity, tau is the torque, and d collects external disturbance. The parameters of the pendulum are given in this table, and we start by defining the state x1 position and x2 velocity. Then the pendulum dynamics can be rewritten as in 5, where x is the state vector and b is a coefficient. By denoting f and phi as appearing here in 6, placing 6 in 5 after that yields representation 7, which is the base of our design. Thus, the observer 8 can be applied to get C2 equals X2 for all time graded equal capital T sub 0, with T sub 0 in the semiopic interval 0 capital T. We will present an experimental study through a comparison with a literature observer. The experimental setup consists of a DC motor manufactured by the Chime and pendulum prototype. An optical encoder with 1000 pulse per revolution provides position. This space is used to get a velocity which is proceeded offline using low pass filtering for the only purpose of evaluating the observer performance. The pendulum initial conditions are set at the origin. Meanwhile, the observer initial conditions are as follows. The torque is chosen as in 9 with parameters given in 10, and the experimental sampling time is 1 millisecond. For the sake of comparison, a prescribed time observer presented in the Holloway and Christic is used for comparison. In the experimental study, the prescribed time Ts equals 1 second, and for the observer in Holloway and Christie, this parameter is extended to 1.005 seconds. The injection terms appear here in this table for the observer in Holloway and Christie with its parameters. Meanwhile, the prescribed time finite gain, let's say our observer parameters are set to alpha and beta as shown here. In this slide, I'm showing you the observation errors. As it can be seen, our observer convergence is at capital T sub 0. Meanwhile, the convergence of the observer in the literature from Holloway and Christie is at the final time capital T, as it can be seen better in this observation error figure. The observation injection terms are shown here. In green color, our observation injection terms, and in red color, the prescribed time observed from the literature. As also, it can be seen that our injection terms are uniformly bounded in the time interval, and the switch time is present here at capital T sub 0. Meanwhile, the observation injection terms from the literature tend to escape to infinity near the final time capital T equal 1 second. This is in contrast with our design where the injection term remains uniformly bounded in the entire interval. This section is devoted to the conclusions. A prescribed time differentiator was developed based on the supertwisting observer design, reworking the hybrid framework that relies on time and state rescaling. Robustness against signal with uniformly bounded second-order derivatives was shown. Tuning guidelines were given to stabilize the underlying system in a specific prescribed time regardless of initial conditions and unmissable disturbances. The numerical and experimental studies supported the theoretical results. The approach admits a straightforward extension to the sequential signal differentiation up to the order n, provided that all signal derivatives up to the order n plus 1 are uniformly bounded. Thank you very much.